Hi everyone, my name is Neha and this is the fifth lecture on Introduction to Automation. In this lecture, we are going to learn about different sensors. The first sensor which we are going to see is the linear variable differential transformers, and this type of sensor is a position sensor. And now we are going to learn about the working of this LVDT sensor. LVDT is the short form of linear variable differential transformer. So this type of sensor, it consists of three windings and a movable core. So inside this you see this core which is movable to and fro, and these are the three windings, two secondary windings. This is the first winding and this is the second winding, and third is the primary winding which is connected to the AC reference voltage. Now in this, the secondary windings you see here, they are wired together in series and they are out of phase with each other. Now if you see the working, what will happen if the core of this LVDT is exactly at the center, then the voltage induced on the secondary coils, they are going to be equal and opposite, giving a net output of 0 volts. So here the C condition you see when the shaft is at the center. So this is the same condition. So voltage applied on the V1 is this. This will when the voltage is induced in the secondary coil 1, then this will produce a voltage V1, and this is shown here. And when the voltage is induced here, then the voltage looks like this, which is the V2 voltage, and you see that these two voltages are out of phase. When the core is at the center, then they are exactly out of phase, and the net voltage produced is going to be 0 volts. Now let's consider what will happen when the core is moved a little to the right. So if it moves to this direction, then there will be more coupling to the secondary winding. So the voltage here developed will be higher when compared to the this secondary winding. So the magnitude of the voltage you see here is higher when compared with the magnitude of the secondary winding one. So the net voltage produced will be like this. Now similarly, if the core is moved to the left, then the voltage induced on the secondary coil 1 will be higher when compared to secondary coil 2. So the net voltage produced will be like this, and this is the magnitude of the voltage, and it is based on the voltage we got in these two. And this net voltage is the net voltage between V1 and V2, and same is over here. So we see here in this case, when the shaft is on the left, the net output voltage is in phase with secondary winding voltage V1. They both are in the same phase. Whereas when the shaft moves to the right, then the net voltage produced is in phase with the secondary voltage produced, which is V2. So they both are in the same phase. So in summary, we can say that the output of the linear variable differential transformer is an AC voltage with a magnitude and phase angle. The magnitude represents the distance of the core, that core which how much it is off from the center, and the phase angle represents the direction of the core. Now here you see the interface circuit for an linear variable differential transformer, and this linear variable differential transformer is connected to the phase sensitive rectifier, further to the filter, amplifier, and here to the reference oscillator. So this reference oscillator, it will provide the AC reference voltage to the primary. So this coil you see is the primary coil of the linear variable differential transformer, which is LVDT. So it will provide a voltage to the primary, which will be typically around 50 to 10 kilohertz at 10 volts or less. And then after that, depending upon how the core moves, you will have some voltage developed over here, which will go to the phase sensitive rectifier circuit. And this rectifier circuit you see here, it has the voltage coming from here and another voltage which is the reference voltage coming from this oscillator. So this phase sensitive rectifier, it compares the phase of the LVDT output with the reference voltage. And if they are in phase, the rectifier outputs only the positive part of the signal. And if they are out of phase, the output of this signal and the reference oscillator, they are out of phase, then the rectifier will produce output only the negative part. So only the negative part of the output will be produced. Now after sending the output signal from the phase sensitive rectifier to the filter, so this filter is a low pass filter. It will smooth out the rectified signal to produce the DC. So you can see here how the signal will look like. So for the positive, it will look like this, and for the negative, it will be smoothed out and it will look like this. So you can see how this waveform has been smoothed over here, and similarly the positive one has been smoothed over here. Now the signal received over here, the magnitude of signal is going to be small, and that's why we have this amplifier which will increase the magnitude of the signal, and then here we will get the DC output voltage. So this was the interface circuit for an LVDT. Now let's move on to the next topic, which is angular velocity sensors. And these angular velocity sensors, or we can say tachometers, they are the device that give an output proportional to the angular velocity, and it is given by this formula. Velocity is the rate of change of position. So velocity is equal to delta theta upon delta t, where delta theta is the change in the angle, and theta 2 and theta 1 are the position samples, and this delta t is the change in time. So t2 and t1 represents the times when the samples were taken. So we will use this formula to calculate the velocity from the position sensor. Now there are different types of angular velocity sensors which are available. First is the optical tachometer, second is the toothed rotor tachometer, and third is the DC tachometers. And these sensors, they are used for different applications. For example, in automobiles, airplanes, trucks, tractors. They are used to estimate the traffic speed and volume. They are used in numerous types of machinery and prime movers. In medical applications also these are used. So etc. These are some of the areas where these sensors are used, and they have their applications. Now let's see optical tachometer. The optical tachometer is a simple device which can determine a shaft speed in terms of revolution per minute. So you see here a photosensor is mounted, and it is mounted in such a way that the output pulse is produced each time when this strip tape is passed through the photosensors. And after this photosensor, you can attach a digital circuitry which will let you know how many times this shaft has rotated, or this disc has rotated. Now on the right you see a real example where a tachometer is used, and you see how the rays are going towards the targeted object, and from there it can calculate the angular velocity, which comes in RPM. Now you will notice here that this system cannot sense the position or direction because it just has one photosensor. However, if two photosensors are used, the direction could be determined by phasing similar to the incremental optical shaft encoder, which we have seen in the previous lecture. Now next is the toothed rotor tachometer. Toothed rotor tachometers, they consist of a stationary sensor and a rotating toothed iron-based wheel. So you see, this is the rotor and this is our sensor element. And in the circuit form, it looks like this. This is the rotor and the magnetic pickup coil is attached in this way. And then from the other side of the transformer, you get the electrical counter output. So in this, what happens? The sensor you see here, we will name this as a variable reactor sensor. So here this sensor, it generates a pulse each time a tooth is passed by, and the angular velocity of the wheel is going to be proportional to the frequency of the pulse. So for example, if the wheel has 20 teeth, then there would be 20 pulses per revolution. Each time an iron tooth, you see here, when it is passed near to the magnet, then the magnetic field within the magnet, it's going to increase and it will induce a voltage in the coil. And that induced voltage will go to this transformer, and from here the output voltage is received. On the right picture, you see the application of tachometer, which can be used in cars, aircraft, or other vehicles, and it is used to show the rate of rotation of the engine's crankshaft. And they typically have markings you see here, which indicates a safe range of rotation speed. So this is one of the example of tachometer. Now let's move on to the next tachometer, which is the DC tachometer. And DC is the direct current tachometer. It is a speed measuring device that produces a DC output voltage proportional to the shaft voltage. So in this type, you see this is the example of a DC tachometer, and on the right hand side you see this is the circuit of a DC tachometer. And let's see the working of this type of tachometer. So you see it has a armature and which is attached to the shaft, and as the shaft of the machine it revolves, the armature of the tachometer revolves with it, and the magnetic field will be produced because you see these magnets which are attached here, and with the help of this a magnetic field will be produced. And you see a commutator which is attached to the armature, and this commutator they will collect the generated current from the armature and then convert the AC EMF into the DC EMF. So that's a function of them, to convert the AC into DC EMF. And the brushes you see here, these blocks you see here, these are the brushes, and these brushes, they collects the current from the commutator and supplies it to the external circuitry of the tachometer. So the EMF induced is going to be measured using a moving coil. You see here a voltmeter is attached here to measure the voltage, and the moving coil voltmeter has a uniform scale, and it is calibrated in speed directly. So the speed of the machine can be measured using this device. Now variable resistor which you see here, it is connected in series and it is used to limit the current. You see a wiper over here, so this will help in limiting the current. So this is the working of DC tachometers. And because of the commutator and the brushes you see here, there is a disadvantage of using this type of DC tachometer. The reason is with time the maintenance will be required for commutators and brushes, because output will become non-linear if the proper maintenance is not done for the commutator and the brushes. So that is the disadvantage of DC tachometer. So this is the end of the lecture. Thank you so much for watching.